In this work, we answer the question, which two-stage planner should you choose for your environment? Two-stage planners, where the front end chooses a homotopy class and the back end further optimizes the trajectory, have gained popularity due to its robustness and efficiency. But their evaluation has been lacking in two ways. First, they are conducted in environments with similar obstacles, like vertical pulls. Second, they are typically focused on overall performance and not isolating the effect of each stage separately. Both shortcomings make identifying the best two-stage planner for a new environment difficult. To solve these problems, we believe we can evaluate the planners separately for different environmental complexities and make planner recommendations accordingly. To this end, we propose an open-source two-stage planning stack to easily integrate new front-end and back-end planners, two new environments to vary environmental complexities, and lastly, an evaluation criterion called ECS that gives a unique signature to each environment and identifies the likely performance of planners. For the open-source planning stack, we took a modular approach so that both front-end planners and back-end planners can be quickly swapped. We select 5 front-end planners with different levels of fidelity and 2 back-end planners with different assumptions on the vehicle dynamics. We run the planners in our proposed parameterized environments and real datasets. To quantify environment complexity, we designed ECS, which describes environments from sparse to dense, dispersed to cluttered, and unstructured to structured. After running the planners on environments with varying ECS, we obtained the success scatter plot for each planner, and additional metrics such as trajectory time and energy cost. We find that integrating dynamic constraints in front-end planner usually has no benefit over geometric planners. Additionally, we find RRT star is almost always the best front-end method, and depending on the sparsity of the environment, we can choose the back-end accordingly. Here we identify a scenario where a higher fidelity front-end is problematic. SST plans in input space, making finding a short and direct solution difficult. On the other hand, RRT star, operating in just 3D, plans a much more direct path. We also exemplify the differences between back-end planners here using real experiments. Gcopter does not use front-end output and only considers polytope constraints, but Outro tries to follow the reference trajectory. Therefore, in a more cluttered scenario, a less dynamic front-end makes Outro more likely to fail than Gcopter. We believe using the ECS is a first step for planner selection for the community.